ciencia ante los retos medioambientales. Tengo a mi izquierda a Amanda Wilson. Amanda Wilson es investigadora británica cuya experiencia principal está relacionada con el microscopio electrónico. Forma parte del equipo de investigación de la biología estructural del Imperial College de Londres y la línea de investigación en la que conecta con el trabajo de Alex y Ana.
Sorry, guys, I just went to the late. Sorry. Okay, so she's introducing your project. Later on, you will talk about it a little bit more in depth. And their project focuses on how molecular machinery of the cell is ensembled, how it functions, and how it evolves. And the main aim of that project is to create a set of molecular tools based on the DNA to characterize pathogens by means of combination of different new technologies. This is what we're going to talk about later. Ana Dumitriu is a British artist who works in sculpture. She also works with crafty means and tools, but simultaneously she is working with bacteria, microorganisms. She's working in scientific research labs in areas related to synthetic biology. And as well as artist and artist in residence of different research labs and research projects. Furthermore, she is president of the section Art and Science of the main association of science in Great Britain. She has exhibited her works nationally and internationally, worldwide. She has received many awards, but what really surprises me out of her curriculum vitae is that together with Alex May, they are the first artists with an exhibition in the greatest and oldest museum of history and science of Oxford University, that artists go there to a museum devoted to science with a collection of tools and with different pieces that take us from the Middle Ages to current age. I think that is an achievement, and that is incredible. That means that art can also go into exceptional areas. A museum of history and science, imagine. So Alex May is a British artist, the same as Anna. He works in a wide spectrum of digital technologies. He works on programming, video mapping, robotics, with all kinds of audiovisual and interactive systems. They both work together, but they also have their own professional career individually as artists. And what they are working on together is the next project we will visit later on. IKEA bought, and many knowledge fields are included here: robotics, biology, artificial intelligence, AI in English, which also plays an important role in this new project. They officially opened this project at the Festival Arte Electrónica. It was one of the highlights. We contributed to the first first phase of this ambitious project. It is a work in progress project, because what you're going to see later on is only the very beginning, the baby steps of a larger project. And for us, it has been an honor and a pleasure to contribute to this project. Gijón, Asturias, LABoral, contributing to such an immense project.
Vamos a comenzar esta parte de la mesa
part of the panel
con una pregunta muy
with a
simple,
simple question, but at the same time very significant question. This was mentioned in 1944 by a physician, a philosopher, Nobel laureate, physics, 1933, Erwin Schrödinger. The question was, what is life?
Una pregunta
very simple.
Simple
question,
curiosa,
she says. A curious question.
Llamativa que lo
Striking,
y
no?
que lo publique.
To see that it is asked not by a biologist, but rather a
Una pregunta que
physics
que ha
expert,
tenido, consecuencias importantes para distintos
and a question that has had many consequences
y de esto vamos a
in
empezar
the
a
different parts of science and
Amanda.
also art. Amanda,
¿Qué es la vida?
what is life?
Hello. So, as you said, Schrödinger addressed this question in 1944, which is quite a long time ago. And he reckoned that life is all about reducing its internal entropy, which is the same as saying it increases order, really. And if it stops doing that, it basically ceases to exist. It dies, I guess, is another way. So some people say that is the theory of life, if you like, but the definition of life. But there is no consensus. So James Lovelock, anyone who's into the environmental thing will know about him, he also thinks it's about reducing entropy, as does a guy called Jeremy England, a researcher in the UK. But there are other opinions, like NASA, who think that it's more about a self-sustaining chemical system that's capable of Darwinian evolution. And I think there are many theories, but those are a couple of the most common ones. I think everybody agrees entropy is part of the definition, but it's not an easy thing. There is no consensus about the definition of life because there is no theory, consensus on the theory of life.
Pero la pregunta era lo suficientemente sugerente para que otros científicos como Crick, Watson llegaron a
try to advance and make headway in the discovery of the double helix, for example, and all of a sudden, in the mid and long run, a new collaboration framework started to rise between physicists and biologists, which fortunately led to an advance in the decoding of the DNA. And thanks to that work, a new fruitful relationship was established between both fields of knowledge that up to then were regarded as impossible to work together, right? Physics, mathematics, and biology, imagine. And the scientific current advances are based on those fields of action, no?
Yes. Yes, so as you said, Schrödinger, he inferred there was an aperiodic crystal, and he couldn't really work out, I think, beyond that with the existing technologies, but later on the structure of DNA turned out to be pretty much just that. And from that, you've got nowadays the genetic revolution, all the sequencing of many, many genomes, including ours. And this has given rise to a very strong field known as phylogenetics, where you're building the trees of life and you can infer things about the past even without fossils.
Yes, after the Second World War, the question, what is life, was a very important question that promoted and strengthened other fields of science, but also other fields of arts. Above all, after the 50s, the 60s, art wanted to melt with life, wanted to learn from life, wanted to abandon a production of objects to somehow enter into a new working dynamic, a working methodology based on processes, understanding art as a process, understanding life not as a game, but rather as a verb. As a biologist, Lynn Argolist mentioned, artists started also simultaneously to understand life and art not as a thing or as an object, but rather as a verb, as a process. How do artists work today, artists like you? Taking into account the concept and the elements of life.
I'll start, because I think it's different for both of us. I tend to work very much embedded in laboratory settings, so I go in and I'll actually do hands-on biological research. So, but it's not really research, it's an artistic intervention. I use the tools to make my own kind of, even conceptual artwork, so using genetic modification, whole genome sequencing, using bacteria, using archaea now.
She can do things I can't do at all.
So there are different ways of kind of looking at this notion of life, and then you bring in the idea of artificial life as well, and what might that be? We don't really have we don't have a definition of life, and this leads us to a problem where how do we decide if we've ever made an artificial life form? Because if we don't know what life is life connected to biology, or is it something that can be separate from biology? It's like a similar question to the notion of consciousness, is the philosophy isn't there, let alone the kind of the science of this. So if we did, using our technologies, create something that we thought was an artificial life form, would it really be? Is for instance, Craig Venter's group, who's a synthetic biologist who creates these kind of almost like basically very simple bacteria which are synthetically created in the lab, but they're made of biological things. Are they closer to life than a robotic life form might be, even if it was fully autonomous and made its own decisions? It's interesting, and a lot of the scientists we're now artists in residence at Hertfordshire University, working with artificial life and artificial intelligence there and robotics. But previously I was at Sussex, and they're very much focused on this kind of questions of when is something alive, what makes life, and there's this idea of autopoiesis, a self-sustaining system of networks and processes that sustains the networks and processes. So it's this thing, and when they've programmed that into like computer software, this idea like as an algorithm, it kind of builds a cell wall, but a kind of digital cell wall. So there are these like really interesting aspects of that. But when I was kind of studying artificial life, I sat in on a course at Sussex, one of the master's courses in artificial life, and there's the course leader, who was Inman Harvey, started off by saying, well, if you landed on a planet somewhere and you saw this pink blancmange, this sort of blob on a rock or something, and you wanted to know if it was alive. How would you work that out? We didn't fully come up with an answer to this, but it's something you can ponder on your journeys home or something. We did decide that it was probably not good to prod it with a stick, because it might eat you or something if you woke it up. But it's this question, and one of the things we talked about was this idea of homeostasis. So that means like to try and keep in the same sort of situation. So like we do that by, when it's hot we sweat, or when it's cold we have the hairs on our skin come up, and that's our body trying to keep within a range. And so there was an idea that probably that was something to do with it.
Mm-hmm. And I think in our work we do all these different robot projects, and we often play with making the robots do things to make them seem alive, because we're working with that perception of our perception of intelligence. What would, if a robot does something and it does it at the right time in the right way, we go, oh, that's really clever, you know. But it's only 1 second away from doing it at the wrong time, and would actually could be a catastrophic failure. So it's really a lot of the time about this our perception of what is alive and what is intelligent, and what is you know. And as artists, we really enjoy playing about with that. With Archaeobot, we've tried to embody a very sort of organic feel. So it seems to be sensing its environment and performing actions which we can somehow relate to, but not necessarily fully understand. And this is how, you know, to go with your blob analogy, sort of, you know, if we saw a thing doing this, if you didn't know it was a robot, if you didn't know it was something that was created by another person, would it be alive? Would it, you know, at least on the face of it, before we start cutting it open and
it's very similar to the so-called Turing test, which is very much misrepresented by the media, because it actually, what Turing said, Alan Turing, who's a famous mathematician from the UK, who actually came up with the plans to build the first digital computer, and he was asked this question about intelligence, what would be an intelligent machine, and he threw it back on the people and he said, well, what would you consider to be intelligent? So people will say, oh, has this robot passed the Turing test? And they're misunderstanding the Turing test, because he didn't say that. He said something that could fool us. So he talked about a Victorian parlor game, like an old-fashioned game, where which, as far as we know, doesn't actually exist. No one can find a record of the game, but where you had to pretend, well, you had to guess whether somebody hidden behind a screen was a man or a woman. And you could only do this by passing notes under the screen. And you'd have this conversation, you could ask questions. And Turing actually said, well, maybe, like, because of our perceptions of like gender stereotypes and things, and famously he was gay and chemically castrated, which led to his suicide, but he was very interested in gender stereotypes as well. Because of this, because of this gender stereotyping, you might have to pass the wrong message. You might have to, if you knew you were talking to a man and you were trying to pretend to be a woman and you were a man too, you might have to say something that a man might expect a woman to say, or even different, like what a woman wouldn't naturally say, something that a man would think she would say. And then he talks about this. So it was like kind of the thing, having enough intelligence, what would you accept to be intelligent? If you could have a conversation with it, would you think that was intelligence? So, yeah, it's very similar. So that's, I think, kind of feeding into the work a lot.
In a project which is dealing...
There is a project called ArchaeaBot, right? A project such as ArchaeaBot that is presenting the challenges and the questions on future life. You at the same time are making use of a very old life, one of the first forms of life. They are the archaeas, right? Primitive form of life. It would be interesting to have Amanda introducing what you are doing with Archaea in the framework of Mara, and maybe because I think that the link between creation and research is the work focused on Archaea, right? And I would love you both to introduce these aspects, to share these links with us.
Yes, with pleasure. So I think maybe first it's appropriate to say a little bit about what Archaea are. So some people have never heard of them to this day, although these two fellows, Woes and Pace, actually discovered that they were a domain of their own. So when you were at school, when I was at school, I don't know about when you were at school, but you had prokaryotes and eukaryotes, and prokaryotes were all the little tiny single-cell swimming-y sort of bacteria type things, and everything else is eukaryote, like plants, lions, yeast, us, everything. So eukaryotes is kind of animals, plants, everything we usually think of. Prokaryotes is now a wrong word. It's no longer scientifically viable because what it actually covers is bacteria and archaea. And although these look very similar superficially, and they both are single cells, they both swim, so you think, what's the problem? But if you look at the information systems that are actually controlling these cells, with bacteria and archaea, they're completely different. And actually, archaea are very like eukaryotes, which is fascinating. So some people sort of semi-flippantly, but not entirely, say, we are all archaea. So that's really interesting, I find. And it's now accepted after many, many years. It took a long time for the scientific community to shift their sort of standard approach to pro and eukaryote. But now, finally, it is totally accepted. There are 3 domains of life, not 2. And you basically have bacteria, archaea, and eukaryotes. And we don't actually know, it's a question mark where archaea and eukaryotes branch off, but they are from one branch. And then you also have another common branch from that where bacteria come off. And that's the point at which you get this initial branching is what's described as the last universal common ancestor. Mm-hmm. And it's all still a mystery. You can only infer, because there's no fossils with these little tiny or very little hard evidence in that way, but you've got phylogenetics, you can extrapolate back and you can imagine to some degree what this ancestor might be like. But it is still essentially, you can't be sure to say this is exactly what it was like. We do think the bacteria and the archaea came together, possibly, to make eukaryotes, but it's more archaea than bacteria. Maybe I'm a bit biased. So now, why are we studying archaea and not bacteria? Bacteria are very well studied. There's many of them. They're known, the motors, a lot of them are already solved. A lot of people know the structure of the bacterial motor. The archaeal motor has a big advantage in that it's only got 14 proteins that make up the entire motor. So the motor is a bit like a little outboard motor on a boat, where you've just got this little whirring thing, and it turns the propeller. Only in this case, instead of a propeller, it's the archella, and you will see a nice example of this when you go into the dark room. So basically, it's because it's so simple that we are tasked in our particular lab, because we're part of a consortium, of actually solving the structure of this archella motor. And in doing that, we're then able to identify some active sites, some little tiny bits of protein. They're not even, we can identify the whole proteins as well. But a crucial part of this particular project is to identify these little catalysts that actually cause the movement, the rotation, because this is the bit that the project leaders are really interested in. And what they want to do is steal these bits from archaea, copy them, and insert them into the DNA scaffold. And maybe just a very few words about the DNA scaffold. This is nothing to do with DNA in terms of genetics. This consortium is not interested in DNA duplication or the Crick-Watson duplication. This DNA is strictly there because of its structural rigidity. It's an established field now to build these shapes. Anna's done it herself. To build these shapes out of DNA. And so they've built this kind of scaffold, which are like the stators, which if any of you have done any motor, if you're familiar with your motor car or whatever, your boat, they're the fixed elements in the motor. And then you've got the rotating part, which is imaginatively called the inner ring. They've got the outer rings and the inner rings. They're given acronyms, but they're like IR. And then, but the interface between those two parts, the DNA isn't going to turn on its own. But if you add these little bits from archaea and then you put in some chemical energy where you can use this molecule called ATP, which is very sort of well known, and that's chemical energy, you put that in and they rotate, which gives you power over, it gives you ability to power them when you want. So I maybe stop there for the moment.
How you got inspired in this archaea prototyping and research and to use it for this interdisciplinary sculpture like object, which is artificially alive.
You'll have to decide that for yourself. I've got a background in working with robotics and artificial life, and I've got I guess I'm more known for and have an even stronger background now in working with microorganisms, bacteria and genetics, DNA, synthetic biology. And when Amanda told me about their research and the acronym, I can't remember what it stands for, MARA.
Yes.
Can you say?
Molecular Analytical Robotic Assays.
So it's even got the word robotic in the title. And you told me you were kind of building little robotic microorganisms, and this immediately caught my interest because the idea of bringing together the microorganisms and my fascination for that and the artificial life together was, I think, what set off the idea. And then we started to learn more about these particular organisms, this Sulfolopus acidocaldarius, which is what you're studying under the microscope. And these are some of the most ancient life on the planet. They live in these, they were discovered originally in hot springs in Yellowstone Park, and they like to live in highly acidic, very warm environments, about 80 degrees, 70 to 80 degrees. Yeah. And that made me start to think about this idea of like the climate, the changing climate, and things like acid rain, pollution, and climate change, but climate change is in global warming, I guess. We got that story drummed into us, so we can't get that it might get colder so much. But so it was that kind of stuff that made me think about that, and then we were talking about the bringing in the robotics and the AI to why not make a robot? And then we were thinking, well, we've worried about this idea of climate change, and the other big kind of contemporary fear, I think, is this fear of the problems of AI, which is quite often misreported, misquoted. Lots of scientists are misquoted on this. Like people like Stephen Hawking is very misquoted about his fears and concerns around AI. But we were very interested in this idea of our concerns about it, and we started to think, what if we put these concerns all together into one robotic archaea life form that brings together this very ancient life, but this very future life as well.
And what do you think about the future life forms? If we don't have really clear what the current life forms are and what life is, what about future life? So we are entering in a very hypothetical area.
I mean, I'm sort of interested in the sort of more digital side, and especially our cultural shift towards integrating digital technologies within our everyday existence and as part of our lives, you know, and as the Industrial Revolution did for our muscles, you know, it created machines that could lift things and make things in a much bigger way than our physical strength ever could. Digital technology is really transcending our physical limits and spreading our mental, emotional sort of essence, you know, out into the world, so we can connect with anyone in the world, you know, immediately and have a conversation like we're having a conversation now. And I like this idea that you know, it's a sort of rapid evolvement, a rapid evolution, and then we're sort of feeding all this information into these machine learning algorithms that, you know, obviously are being siloed by companies like Google and Facebook and things, and are, you know, there's plenty of good use that will come out of them that will benefit society as a whole, but there's equal amounts of harm that can be done, and control, and the idea of sort of profiling people and being able to know what they're going to do next and how to influence them is obviously a new level of global control that we've obviously never had to deal with before. So it's even in the sort of near future of future life, our own existence is no longer just this physical space that we take up, but our digital footprint, which spreads around the world and over time as well, because everything you put online is in theory there for a very long time. So from your baby pictures to your Facebook death page, it's you know, you're just as present there as you know, at any point in your life. So it's a really interesting breakdown of the idea of being alive, of being alive at different, you know, for a period of time, and being alive in a particular locale, and you know, so it's moving so rapidly that we're all struggling to sort of keep up and deal with it.
It's clear that the border lines between artificial, natural, organic, and non-organic are somehow breaking down. They are matched in very different new constellations. In your case, you are working with robotics. You are working with inspired by in Akeabot, inspired by the structure and the function of Akeas. You are working with the artificial intelligence system, and what we are seeing here already evolved since it had been presented for the first time at Ars Electronica. Could this system preserve the artificial intelligence for the future, or how do you think it's just a hypothetical visualization which should inspire us, or what are the other concepts behind which could be also useful for you as a scientist? Or there should be something useful, because if not, I can't imagine that you would enjoy collaborating as you are doing. So tell me about that.
I think in terms of the kind of the preserving artificial intelligence, I mean, that it makes me think about is that kind of transhumanist idea of uploading. So the idea that we might be able to live on after death by uploading our consciousness. If we could work out what that might be, we could build some sort of intelligence and upload our consciousness and live in kind of a computer system immortally. There are people researching this.
I think I've seen something somewhere about like being able to, some small aspects of consciousness have actually been able to kind of be stored and then reinserted or something. I can't remember the details.
We can definitely interface with neurons and things like that. So there is potential. I worked with scientists at Sussex who were kind of building electrical arrays that you could build work out what was going on in the neurons. So there's this potential for kind of being able to upload your consciousness. So I was wondering if we were able to actually, the robot is currently built out of, it's 3D printed, made of PLA, but if you could make it out of something that would last better in these environments, maybe what the archaea are really made out of, you could perhaps use that as a material to coat it, or, titanium springs to mind, but I'm not sure I've got the budget yet. And maybe we could even live on with our uploaded consciousnesses inside an archaea bot and be embodied so we could interact with the world. And you might see that the archaea bot's already started to explore its environment now. We've just noticed it's been picking up rocks and moving them, which is strange. I'm not even joking, it's really doing it.
Yeah, we didn't tell it to do that. So, we're not worried yet.
But anyway, I saw, I know I'm noticing a difference between the first version, I saw it as electronica, and the one we see here. So you are working on an ongoing project. What are the next steps? Because after this EMAP residency, you will go on. You are collaborating also, the Art Council, British Art Council is collaborating with your project. You are working with them. What are the next steps? And what do you want to reach, or where you want to go with this project?
So the initial, as Karen said, this is a prototype that we made here in a residency. So we've still got quite a lot of work to develop the structure, and we want to put LEDs inside of it and get it to make sound and have all these sort of external ways to communicate. And obviously keep up with your research and feed in any sort of latest developments.
And build an S layer.
So
a transparent S layer.
The structure you'll see is actually the inner layer of the
cell wall.
The cell wall with the sort of motor structures
embedded. Exactly, yes.
But there's actually an outer layer which would kind of hide all of that, wouldn't it?
It could be see-through.
It is actually an open mesh. It's a bit like chainmail. It's quite unusual, and archaea are quite rigid, so you can't lyse them like you can bacteria, because the cell wall just shrinks and leaves this hard outer casing, and that's actually given us a bit of a headache in the lab, but I won't go into the details. But you can't just make them smaller, which would be good for microscopy, by lysing them, which is a common trick. You also can't make mini cells, which is something that they do with bacteria routinely for what I do, which is electron cryotomography. And it's just to do with the electrons being able to penetrate right through the sample. If it's too big and fat, it's sort of game over. You cannot get to that structure. But we have some tricks up our sleeve still, so we're including a different organism. So maybe we could build one of those as well. Yeah. Halopharax volcani, I know you know, but which comes from the Dead Sea and lives at more like 40, 45 degrees and lives in a very salty, if anyone has been swimming in the Dead Sea and you can just float. Unfortunately, they're actually becoming extinct. because the Dead Sea is becoming more and more salty as they're shorter and shorter of water. And even if water's pumped upstream, there's no guarantee that that will preserve the ecosystem as it is now. So they're what make it red sometimes. They're red archaea. Now the nice thing about those is they have archaea just where we want them. So I won't say more, but yeah.
And the last question from my side, maybe afterwards you would like to make also other question. I really would enjoy to, if you would use our meeting here to address some questions to our to all of you. How is the situation, the collaboration between scientists and artists in Great Britain? Because as far as I know, the collaboration between art science are much more regulated and often seen. Your artworks are shown in science museums, but also in big national, international art, contemporary art exhibitions. How is this situation in your country?
Well, I guess I could.
Yeah, you probably know more about this than me. I mean, there's that lecture.
I think it is quite a privileged location to be working in this field, but then there are sort of, chicken and egg situation where, what comes first. There's a culture in the UK of this kind of maverick, eccentric person anyway, so we're kind of quite accepting of that, and scientists and artists, they kind of see quite, as you were saying earlier, see quite eye to eye on a lot of aspects, and this, I think, is a bit more explicit, but also groups like the Wellcome Trust, which is one of the largest medical research charities in the world, funded a lot of art science collaboration, and they kind of got the word out quite a lot, and there's a science gallery network as well, which we work with, who exhibit art that's to do with science or inspired by science in some way. And I think even it's interesting that even like the Arts Council, the V&A Museum, or places like that are very much exhibiting their funding and exhibiting art science collaborations or bio artworks or robotic artworks. So there's quite a platform for this. And as you mentioned, we had cybernetic serendipity in, I think, 69 or 71? I can't remember.
No, 69.
And 69, yeah.
And C.P. Snow, who talked about the two cultures at Oxford very early on. And so he maybe initiated that thought, what is the difference anyway?
Well, yeah, he talked about the problem, and he sort of created the problem as well, because people often reference this idea that there are two cultures, and he wasn't exactly talking about it like that.
No.
If you look
again,
at
it's a misquotation.
Yeah, it's an interesting thing. So people think that there are these separate disciplines, but actually, I mean, the idea of science and art being separate disciplines is
new.
Quite recent.
Yeah, Leonardo.
And back to just a few hundred years ago, you would have people who were working across both fields. So, for instance, Robert Hooke, who was very influential in the Royal Society and in microscopy, the real forerunner, he was doing artistic works as well, drawing these incredible drawings of fleas and things like that. So it's always been very much kind of collaborative. He also designed some of the churches and worked with Sir Christopher Wren, who built St Paul's Cathedral. So he was integral in rebuilding London after the fire. So there didn't used to be this kind of divide, and it was a bit of I think it's always considered a bit of a false divide. There's also the idea that it's actually become, I think in the UK, quite fashionable to be collaborating with an artist. So scientists actually want to be collaborating with artists, and we both get approached, don't we, quite often now, so for collaboration, but not just in the UK, internationally.
Can I say a quick word? I think what's become established, and I'm not sure how many scientists are aware of this, but ironically it's a fact that people don't listen to facts. but they listen to stories. And I think, I'm not saying art is a story per se, but it's a different manifestation. It's not just saying, these are the facts, soak them up, because it's good for you, or something. It's exploring facts and understanding. So as well as the fruitful collaboration in terms of both parties being able to advance their own careers or their own research, it's also a different way of conveying information that is quite powerful in itself, that goes beyond just listing out what the facts are and then hoping, because even if people will understand, I think it can be phrased in a way, and people aren't stupid, so you can read it and understand, but it just kind of goes, whereas we've evolved to understand stories, to look at images, and that's what we've naturally evolved to do. So for us, that's actually more natural. So it's an excellent way of communicating, and maybe intuitively people understand that, even if they don't understand it in a literal way. So that's what I think is going on now.
I think it's almost a political thing. It's sort of politics with a small p, not related to a particular party or anything. The idea that the wider public should have access to the science,
publicly
to the
funded,
debates, not just publicly funded, but just to be able to participate in debates about the direction of science, and particularly medicine. This is a big interest of mine, and which really affects them, especially like microbiology, clinical microbiology. It's right there affecting everybody on a regular basis, and if they don't understand the nuances of the issues around it, then they're subject to basically advertising, people selling them things. You can't make a decision between a good solution to something and a useless solution. This idea of using these antiseptic hand gels all the time, not necessarily helpful as well, because they can increase other bacteria living in the hands and things that actually can make things worse in some situations. So it's kind of interesting that you're sort of subject to these other influences, which might not be necessarily positive influences. So I think from an artistic perspective, something we're really interested in doing is bringing that information out and those stories out of the lab and showing how fascinating it is. And you've just done a big collaboration at the Crick Institute in London, and
the Francis Crick Institute.
You had this like big interaction with all the scientists there.
And the first line of the proposal for the Mara was actually antibiotic resistance requires radical new strategies. And it goes on from there. So that's a long-term sort of aspect of this, as well as how do you control bacteria in a completely different way, because they're becoming resistant to the existing approaches. So it's another way of potentially looking into the future and saying we can do this maybe instead.
And in your work at the Crick, it was about the people as well.
Yeah, so the Francis Crick Institute is an enormous new centre of genomic research in the UK. It's 1,200 scientists working at the cutting edge. There's Cancer Research UK, there's Imperial in there. There's, Welcome. There's and the sort of state-of-the-art labs and everything, and it's and I was invited into or commissioned to do an artwork there, which would represent the workings of this place to the public outside, which, as you can imagine, would be quite a complex thing. And it took me 18 months to create this artwork, which is in the front window of the building. And what I sort of distilled it down to, because I couldn't even explain in any detail any one kind of research or any one project or any one technology, so I was really trying to get a grip on the place as a whole, and what became very apparent to me was that it was really about the people doing science, that when we hear about science, we hear about it on the news, we hear about the latest paper or something in Nature. There's some names at the top, and then all the information about science. But this does not represent the effort that has gone in to any one of these things. There's hundreds of thousands of people pipetting and performing endless day in, day out experiments and gathering data and building up this information so these leaps can take place. And I thought that was a really nice thing to connect with the people outside, that it was people inside, curious people inside doing science, and that seemed very relatable to me. And that was became the sort of key message from that artwork.
Thank you very much. ¿Tenéis preguntas, comentarios, sugerencias que hacer a nuestros invitados? Sí, por favor.
I am currently working with marine animals. I am currently working with marine invertebrates, and I should like to know what are the main difficulties to study this special or cryptic group. And another question is really a different kingdom?
Oh, are you asking, is it really a different kingdom? Did you say? Yes, it is definitely, it's quite established now that it's a different, if you look at, I think one of the pictures here actually demonstrates, the one before that, you have to wait for another 16 now. But the difficulties, they're unique for every type of bacteria and archaea. Each one brings new challenges for electron cryotomography, because I don't know if we've got time, and quickly describe what we do is we take them very near native and in situ, so that means they're as close to life as we can get them when we're imaging them. So we don't use chemicals, we don't use resin, none of that stuff like from the old days. It's all done with cryo, which gives you very low contrast, but if you collect enough, you can sum that. And also now we have direct detectors, we have all this equipment that really helps, but it's still very challenging because you're taking a tiny bit of the liquid culture, you sometimes have to concentrate that, and then you're pipetting it onto grid and you snap freeze it as fast as you can in liquid propane ethane, and then you insert that into the microscope while it's still cold on a special stage, and it's kept at that temperature. But the problems are, each buffer brings its own challenge. The buffer is the stuff that the bacteria are growing in or the archaea are growing in. And Sulfolobus, the problem is it's round and fat, and it doesn't actually have that many archella. At first they thought it had a lot, but they're very long, so they wrap around and it looks like they're coming out everywhere. But when we started looking in close up, it turns out it's just maybe none, or one or two, maybe three if you're lucky. And when you put them on their side, when you pipette them, they just land on the grid, however. And it's very rare you get a motor in the right position to image effectively. So that's why we were trying to shrink them and burst them and so forth. So now we're also trying to multi-arcuate them, and there's a whiff of possibility we can do that by adding some chemical. But the other thing we're doing is looking at Halifax volcani, this other organism, because it has these polar bundles, it's rod-shaped, so it's only half a micron at the business end instead of 1 micron. So it falls over on its side, it has this nice bundle of archella, and so in theory it will be quite tractable. We have a student now come from the German lab where they're experienced at growing these things because they're a little bit tricksy. But I'm hoping that it should all just fall into place, so cross fingers. Does that answer your question? Good, thank you.
¿Alguna pregunta más? Pues muchas gracias. Estamos bien de tiempo. Ahora en 10 minutos a las 7:30 vamos juntos a ver la instalación, que la tenemos justamente aquí al lado. Thank you very much for your interesting contribution to our art science discussion. I think we can stop here and go together and see the installation.
Thank you for coming.
Thank you very much.
Thank you.